Okay, I'm grateful to the organizers. Thank you for inviting me and putting this on. I really enjoy the environment here. I'm going to talk about long-range minimal models, and things will make more sense if I start off by talking about the long-range Ising model. So I'm going to start with one of my earlier papers and work my way up to my most recent paper. And one thing to note is that Fanny Eustachian is applying this year, so she will be a name to look out for. She did a great job on these calculations. And long range is a synonym in this context for non-local. And people in different communities can define non-local in different ways. In a quantum information community, you might say a non-local QFT is something where entanglement entropies satisfy a volume law instead of an area law. But for me, a non-local QFT is going to be something without a stress tensor. So there is going to be no conserved local operator of spin 2. And fortunately, in this audience, there are people who see non-local QFTs all the time, because one way to get them is to restrict to some d-dimensional defect in a higher dimensional space. So it's well known that in a defect conformal field theory, the operators that live on the defect itself obey the axioms of some non-local conformal field theory in a lower number of dimensions. And one example of this that's very basic and also very important for everything I'm going to say is the trivial defect in RD, where d minus 2 over 2 is equal to the dimension of some basic operator on this trivial defect. So this is how you get a generalized free theory. And just to remind you of what that is, it's something where the 2-point function has a power law that you choose. And then all higher point functions are given by Wick contractions. And the local description of such a theory is as a defect where, in general, if you want to be able to get all generalized free theories, so for whatever power law you want, you're going to need the higher dimensional space to be a sort of artificial construct where d is fractional. Yeah.
What's the typographic picture of that defect? Because these theories are frequently considered, however.
Exactly. So another local description is by doing a Weyl transformation of this defect to map it to the boundary in some ADS space. And then it's the mass of the free scalar in ADS that gives you this dimension. Yeah, it's sort of the usual thing. And once you know this local theory, this non-local theory, you can generate others. You can take any local CFT that includes some relevant local operator O. And then you can couple it to generalized free theory, where delta chi is d minus the dimension of O minus something positive, so that chi times O is relevant. And then you can use this interaction to trigger a flow to the infrared, which often reaches a fixed point, and therefore gives you another non-local CFT. So non-local CFTs came up long before anyone was using this language, because in '69, Dyson wrote a paper about a certain non-local spin chain, which we now call the long-range Ising model. And the Hamiltonian for it looks a lot like the one for the usual Ising model, except you don't just sum over nearest neighbors, you sum over all the sites. And you allow interactions to decay with this type of a power law. And what he showed is that even though a lot of spin chains at the time did not, which were one-dimensional, did not have a second-order phase transition, because of the all-to-all interaction here, this actually did have a second-order phase transition. And in modern terms, what we would say is that a 1-by-1 stress tensor that is traceless is 0. So if you have a second-order phase transition in one dimension, if you have a one-dimensional CFT, then it has to be non-local. So this was an exciting result, and it was the first of many papers on the long-range Ising model in the early days. In particular, there was one by Fisher, Ma, and Nickel, who developed a continuum description of it, very similar to what Wilson and Fisher did for their phi to the 4 interaction. So in their setup, you take, yeah, I'll write this way. You take this non-local action, which has the same power here. So this is in 1D, but in higher D, you would conventionally write this as D plus S. You take x minus y to the D plus S here, which gives phi a UV dimension of D minus S over 2. This turns out to be nothing but the action of generalized free theory for delta chi equals D minus S over 2. So GFF is a non-local theory, but it is a Lagrangian theory. It just has Lagrangian that you have to integrate twice. So what they wanted to do was take this and then add your standard phi to the 4 interaction in order to reach a non-local fixed point. And this flow is perturbative when this operator is nearly marginal. And another way to say that is that epsilon, defined in this way, should be small. So we can draw a diagram here, which starts at S equals D over 2, so epsilon equal to 0. And starting from this UV, we can trigger a flow using phi to the 4 to reach a line of non-local fixed points that are parametrized by S. So this spin chain, it has a second-order phase transition for any S in some interval. It's continuously varying. And it's intuitive looking at this that if you make S large enough, then this profile becomes very sharply peaked, and the all-to-all interaction starts to look a bit like a nearest neighbor interaction. And you would hope that this starts to recover the same physics as the local Ising model. And there is a non-local CFT you can write down that's close to the local Ising model in some sense. So what you can do is you can take this type of term where now the UV dimension is D plus S over 2, so you change the sign of S. Then you can take the short-range Ising model in D dimensions. So here, the scare quotes will mean that there is not necessarily an action for this theory, but you just take the tensor product of two theories. You're allowed to do that. And then you add this kind of coupling I was writing before. So you take the spin field times chi to trigger a flow. And this has a different regime of validity. So you would define this parameter. Defined in terms of the Ising spin field dimension, which is 0 when this is marginal, and much less than 1 when this is weakly relevant. And that would allow you to start from some large value of s, so bigger than d over 2, and generate RG flows with sigma times chi to reach a non-local fixed point. And what we conjectured in 2017 is that the fixed point you reach either way is going to be the same, so that these lines are connected. And there are three main pieces of evidence for that. So the first is that if you take this theory and you integrate out chi, you generate a non-local effective term with sigma, and it turns out to be a product of sigma of x and sigma of y over exactly this thing, x minus y to the d plus s. The next piece of evidence comes from looking at protected operators. So I called this the UV dimension of phi before, but it's actually the IR dimension as well, because this kinetic term for phi is non-local, whereas the interactions are all local. So they're not going to be able to generate any multiplicative renormalization for it. So phi is protected. You have the anomalous dimension of phi is 0. But then you can use, you can vary with respect to phi to find an equation of motion, and you get a non-local equation of motion, which can be written in this way. Which relates the dimension of phi to the dimension of phi cubed. And that means phi cubed is protected as well. Its anomalous dimension is not 0, but it's going to be epsilon with nothing at higher orders. And there's a match because you can look at this theory now, observe that chi has a non-local kinetic term, whereas the interactions are local, and therefore deduce that chi is protected. And there's similarly an equation of motion here. There's the one where you just change s to minus s, and see that the dimension of sigma has to be related. And now the anomalous dimension of sigma is just this parameter delta to all orders. So there's a matching of protected operators. But the real clincher came from noticing that if you want sufficiently large S to give you the Ising model, the short-range Ising model, you would need there to be some other operator content in order to preserve the counting of states. Because the local Ising model has a stress tensor. It has a conserved local operator of spin 2. And the conservation of this operator needs to break as soon as you turn on the coupling. And that means that for infinitesimal coupling, you need to be able to write some kind of non-conservation equation like this, where this has precisely known quantum numbers. The dimension and spin just go up by 1 and down by 1. And in the local 2D Ising model, there's no operator that has these quantum numbers rigorously. In the local 3D Ising model, there almost certainly isn't. The errors in the numerical bootstrap would have to be huge to actually have this. And yet, as soon as you introduce this generalized free field chi, you can write this down. You have some coefficients that make it a primary. I think they're just the dimensions themselves. And then you're able to go from a decoupled theory, which has a short multiplet and a long multiplet that combine when you turn on the coupling to become a single long multiplet that's not conserved. So that is our evidence that these are really two descriptions of the same non-local CFT. And they have complementary regimes of validity. This flow is short when this flow is long, and vice versa. So it's a weak, strong duality. Yes. So here you have a single GFF. Here you have a GFF plus short-range icing. And then this line is long-range icing. So the generalized free field, it becomes like you're varying S. So this scaling dimension is always d plus S over 2. But its correlation functions are not going to be given by Wick's theorem anymore at the fixed point. So you'll be able to write down correlation functions perturbatively, for example. At 0th order, they'll become Wick contractions, and then you insert, you add integrated insertions of sigma chi, and then they become more non-trivial. No, at the long-range fixed point, you also have chi. It's the analog of phi cubed, which you have when you go to the fixed point in this theory. And so one good thing would be to see this on the lattice in Monte Carlo simulations. If you look at subleading terms, in the sigma correlation function, you should see some higher order effects due to chi. I think this has not been seen yet, but it's a prediction. And once you know about this duality, there are two main directions you might think of taking. So one is to keep looking at the same model, which is the long-range icing model in dimension 2 or 3, and push things in order to also gain some non-perturbative understanding of it. And this is something I did, well, a couple of papers, but most notably in 2023 with 3 great collaborators, one of whom is here. And then the other direction would be to try to find analogs of this duality, which allow you to bring more non-local models under control. And that will lead to what I have to say about Virasoro, about long-range Virasoro minimal models. But one thing that should be highlighted is a recent paper, well, 2 recent papers, which study the 1D case of long-range icing, where things are very different. The problem is more difficult. And I believe next week we're going to have a talk by Edo Laria on this. So I won't steal his thunder. You'll have to wait until Friday to hear about this. But I will talk about long-range icing in dimension 2 and 3 non-perturbatively, and I'll talk about long-range minimal models. So I mentioned that there are these non-local equations of motion, which relate dimensions of phi and phi cubed, or relate the dimensions of sigma and chi. But they don't just relate scaling dimensions, they relate OPE coefficients as well, because these equations of motion are integral equations, and you can insert those integrals into correlation functions and see what you get. And doing that for 3-point functions gives you these exact ratios, where there's this normalization R, which changes along the flow. It's coupling dependent, but it's independent of the quantum numbers of this third operator O. And that means it's a useful thing to use in the numerical bootstrap. And then there's another analysis you can do, which tells you that R is actually something very physical. So instead of using the equation of motion and correlation functions, what you can do is consider a crossing equation in the presence of a defect, because remember, long-range Ising model is a defect in a fractional number of dimensions. So it starts off being generalized free theory, and then you add some interactions that are localized on the defect. So what you can do is consider a 3-point function which has 2 bulk operators and 1 defect operator, and equate the bulk and defect channel expansions. And because the bulk field is free, it has to obey Laplace's equation, and you find that only 2 modes can appear, only 2 defect modes, as you bring this close to the defect, can appear in the fundamental field. So these are phi and phi cubed. Let's write it this way. So x is 2 or 3-dimensional, y lives in a fractional number of dimensions. And because this field is free, and this operator O is generic, we know that the right-hand side has to be regular, because everything here except the identity is a double trace. So there'll be no singularity as x1 is brought closer to x2. There would be a singularity bringing x1 close to x2 when you exchange the identity, which is not a double trace, but the identity has no overlap with an operator here. This 1-point function would be 0. So this side is manifestly regular. And yet the regularity on the left-hand side is not manifest, so it has to be imposed. And that's what gives you relations. And it gives you relations involving the OPE coefficients, but also the bulk to defect OPE coefficients here are going to make an appearance, because this is the defect channel expansion. And so what you find is that this is a ratio of the 2 bulk to defect coefficients. So the Taylor coefficients with which the phi and phi cubed powers appear as you expand in y. And these bulk to defect OPE coefficients are in turn known in terms of the bulk one-point function of phi squared. So what you can do is use a phi squared as a parameter that you scan over in the numerical bootstrap while imposing these exact relations in order to derive some bounds in a multicorrelator system. So the right multicorrelator system would be these 4-point functions and then the mixed one. And this will take some explanation, but what I'm plotting here, well, what I'm sketching is a plot of the bound on the first unprotected operator of spin 0. So not phi itself, not phi cubed itself. These scaling dimensions are being put in by hand. But the first operator that phi or phi cubed OPEs will be able to exchange that has spin 0. So for each value of a phi squared and each value of s, which determines these dimensions, I'm making a bound on this guy. And if you set s to be very close to d over 2, so something where this first flow by phi to the 4 is weakly coupled, then you end up getting this very sharp spike, which is close to a phi squared equals 0. So maybe I should write the axis here. Then when you start to move s away from d over 2, the spike is not quite so sharp. So you'll get this kink, which is a bit lower than what it was here. And then you'll get a second kink. If you keep raising s, this region will become wider and wider, and so on. And by comparing with perturbation theory, it really looked like these kinks were describing the long-range Ising model. And then you can also do perturbation theory from the other side, because there's the sigma chi flow, which becomes weakly coupled there for large S. And we did some two-sided Pade approximants, and things appeared to be consistent. And I'll say more about this later on, but I want to talk about the other direction, which is looking at dualities like this that could appear in other long-range models, namely the Virasoro minimal models. So are there any questions about where this is going? Numerical. Yeah. So what's the analog of the generalized free theory deformed by phi to the 4 when you want to study long-range minimal models that are not the Ising model? Well, it's been known for a long time that there's a Landau-Ginzburg description of minimal models, first found by Zamolodchikov, where you have the standard kinetic term, and then you skip a lot of potentially relevant deformations. You skip phi to the 4, you skip phi to the 6, and you go straight to phi to the 2m minus 2. So it's a very finely tuned RG flow for a multi-critical model, as we expect. Yes, I should write that, thank you. So recall that in a Virasoro minimal model, the central charge obeys this relation. So a unitary Virasoro minimal model. Central charge has this relation where m is an integer that's at least 3. So 3 is the critical Ising model, 4 is the tricritical Ising model, 5 is going to be the tetracritical Ising model for me because I'm only going to consider diagonal theories. Otherwise, it could be the Potts model as well. Critical 3-state Potts model. And all Virasoro primaries have conformal weights, which are given by Katz's formula for integer values of R and S, which is this. And in the sum identification. And this is a Landau-Ginzburg description of short-range minimal models. And what you would want to do to make things long-range is sort of the expected thing by now. You would say that you now have these two integrals. And now it's d plus s, so it's 2 plus s. And then there's a straightforward duality that you would expect. So phi in this Lagrangian is the lightest operator, the lightest primary operator. The heavier ones are all built up by taking powers of phi. So you would expect that the Virasoro primary, where you're close to a short-range minimal model, where you're just some deformation away that makes it a little bit long-range, you would expect that it would couple a generalized free field to the lightest Virasoro primary here, which is phi 2, 2. So a way to write that is to take this non-local kinetic term. We add this local Virasoro minimal model. And then we say that their deformation is the spin field, which is phi 2, 2 times chi. And this should give a weak strong duality. They flow to the same fixed point. One description is weakly coupled when the other is strongly coupled. But now there's an extra parameter in the game. In particular, we can ask what happens when we take m to be large. Yeah, so I'll erase this. So for m going to infinity, two things happen. So one is that from the Katz formula, it's easy to show that the dimension of phi 2, 2 becomes very small. And then also for this phi to the 2m minus 2 to be marginal, so for it to have dimension 2, then this little delta phi, well, that has to also be much less than 1. So that's a bit different from what we saw with the long-range Ising model. We were going from a phi to the 4 being marginal, so this would have dimension d over 2. So in 2 dimensions, it would have, sorry, d over 4. So we would go from a dimension of 1/4 down to the short-range end, where this would become the spin field. So it would go from dimension 1/4 to dimension 1/8. So there'd be some order 1 shift. now when m is large, we're seeing that it goes from a tiny number to another tiny number. So we could imagine that the flow is much better behaved. We're going, if we try to approximate the strongly coupled end with the weakly coupled end, we might actually find that things are still weakly coupled enough that we can actually check the duality and get unprotected anomalous dimensions to match. So this is a question we asked, and the answer turns out to be a resounding no. It is not possible to recover the anomalous dimension from one end using the other end, even when m is large. In fact, especially when m is large, it's problematic. That's sort of the worst case. Yes. So you mean more options than just phi 2 times chi? Exactly. So you can define long-range minimal models in more ways as you raise m. That's right. It changes in quite drastic ways. So we only looked at the most tractable cases, which are phi 1,2, phi 2,1, and phi 2,2. But they're all quite different. So yeah, that's part of the talk. Yeah, different large m behavior. Yeah, for m equals 3, they're the same. 2, 2, and 1, 2 are identified. But when you move away from that, they're different. It's weakly irrelevant. Yeah, so yeah, remember we're looking at lines of fixed points because long-range minimal models, like the long-range Ising model, are parameterized by S. And for S near one end, this is a short flow. For S near the other end, this is a short flow. A non-invertible symmetry, yeah. Yeah, because they have special OPEs, which keep you in the 1, S or S or R, 1 subsector. Yeah, so this, yeah, so some of the results we got seem to be quite nice, and you can interpret, yeah, then the non-invertible symmetry provides an interpretation of why the results were nice. And a spoiler is that we don't know a duality like this that would apply yet. When we change this phi 2,2 to something else, then this is valid for large enough S, and it becomes harder to figure out what becomes valid, if anything, for small s. But yeah, I'll say more about that when discussing future directions. So I want to say how we checked that these fixed points which look close by when you just consider the spin field's dimension are not close by in the sense that matters. So starting from this phi to the 2m minus 2 Landau-Ginzburg end, you can write down a beta function for lambda. And we got, so in general, you would get very messy numbers where a and b are finite sums where the number of terms depends on m, where the number of terms grows with m. But fortunately for large m, you can find saddle point evaluations of them. And then we got a beta function. We plugged its fixed point into the derivative of the beta function to get sort of one of the easiest anomalous dimensions, so the dimension of the deforming field itself. And at the first order, it's something universal, just telling you how this weakly relevance operator becomes weakly irrelevant in the IR. And then, if you'll indulge me, you get something like this. And the only important point is that when you use Stirling's approximation on this coefficient, you find that it's power law divergent for large M. And that means that perturbation theory is sick at large M. So if you wanted to set epsilon to some small parameter, oh, by the way, if I didn't even define epsilon here, but if you define it such that this lambda has mass dimension epsilon, as we usually do, then you're going to want epsilon to go to 2, even though these are small numbers. So if you want to set epsilon to be close to 2, or even if you want to be more modest and just set it to be 10 to the minus 3, like we usually do in the epsilon expansion when we're trying to get some numerical approximation, there's going to be some large enough m such that this no longer works. Oh, that is where the yeah, okay, I should say it's where this UV dimension, so where 2 minus s over 2 goes to 2H22. So this has a protected scaling dimension. You would start off at some value of s such that this is marginal. And if you raise the value of s such that this becomes relevant, you can keep raising it until this dimension of phi becomes what you expect at the short range end. So I just defined epsilon in terms of s such that s going to this special value that makes 2 minus s over 2 equal to 2H22 corresponds to epsilon becoming 2. So that's a separate limit. You would say what value of m you care about first. So this H22, it would go as it goes as like 1 over m squared, if you're interested in large M. And then you say s has to be very close to 2 for this number to go from something finite to 1 over m squared. And s being very close to 2, well, you can define epsilon however you want. I defined it such that s close to 2 makes epsilon close to 2.
Why for like intermediate m you wouldn't additional 5 to the 12 contraction terms?
So you would if you wanted to flow to a different minimal model. So these multi-critical models have many relevant operators, and they all have to be tuned away for you to reach that one, instead of something lower like the tricritical or critical Ising model. Yeah.
They should still be weakly relevant.
Well, not necessarily. If you put m minus 1, so half as many powers here, you should get something close to dimension 1 instead of dimension 2. There are relations between the crossover value of s and m. But s is still a tunable parameter that labels which long-range model you're in.
Epsilon can be defined for relation to s and n.
Yeah, so before in the icing case, I was writing epsilon is 2s minus d. And now this relation is going to change. It's going to have coefficients that depend on m. Oh, wait, yeah, no longer 2s minus d. Yeah, that's right. And it becomes relevant enough to turn the dimension of this into H22 when epsilon is order 1. But what I'm really just trying to say here is that there's no way to take some random operator in this theory, take m to be large, and then use perturbation theory to recover some exactly known scaling dimension in the solution of Virasoro minimal models. So checking the duality at that level is not going to work at large m, at least when you use this power law to find the 2m minus 2. So now we can try doing the other type of perturbation theory. We can try perturbing around a more abstract CFT, where we have to use not Feynman diagrams anymore, but the recipe of conformal perturbation theory.
Is the reason that the fixed point isn't the small lambda? Which you calculated wrong? I was confused.
Well, I'm taking the fixed point for lambda and then plugging this back into the beta function. So this is, yeah, I guess that's the way to say it. Lambda turns out not to be small because of what these coefficients are.
The same thing happens in non-unitary perturbations. You can't use beta functions to calculate the flows for some non-unitary flows, where you can, but the unitary ones won't. It's the same sort of thing. It's just not determinately close.
Yeah, well, the interesting thing here is that it would look perturbatively close if you did one loop perturbation theory instead of two. Yeah, this is where the problem shows up. But that's perturbation theory around one end. We can talk about perturbation theory around here. So maybe just like a lightning review. In an abstract CFT, if you want to figure out what an endpoint function is at finite coupling, what you do is you insert some exponential of the interaction at zero coupling and then Taylor expand. And importantly, this has to be a bare coupling when you start off. And in particular, if you take the 2-point function of O, you'll get 1. And then you'll get the integral of a 3-point function. And that integral of a 3-point function is going to diverge. It's going to have a UV divergence, which you can regulate by saying that points never become closer to one another than this distance a. And then I think you're going to get pi. The OPE coefficient times log a times g naught. And the way to deal with this is to use the fact that the renormalized coupling is different from the bare coupling, so that you get the beta function. So this, you can say that this operator has dimension d minus delta, so it'll generate this. But of course, when we take some z2 odd operator phi times another z2 odd operator chi, this 3-point function is going to vanish by symmetry, and we're going to have to go to the next order, which requires us to integrate a 4-point function. And it's a regulated integral, which means we subtract terms that diverge as powers of a times g cubed. Logarithmic divergences here will be a sign of mixing. And yeah, I might get to an example of that we saw. And then similarly, for anomalous dimensions, things start off as being some OPE coefficient. And then there is a 4-point function that you have to integrate. And these are the calculations we have to do if we want to explore perturbation theory around this end and see what it looks like for large M. So I can write down some basic results. Something we did in 2017 while exploring this duality thing for the long-range Ising model was we got this beta function which has a real fixed point. So for delta positive, so a weakly relevant deformation, g squared is positive, so that's good. If we take M to be large, we can write down something nicer. So something over M squared times g cubed. But what we did to get this was very brute force. So at first, we had these difficult integrals to do of 4-point functions, where the 4-point functions are built out of Virasoro blocks. And the Virasoro blocks obey BPZ differential equations, so we can figure out what they are in a series expansion to high order, and then integrate numerically. So what we had were plots of this coefficient of g cubed in the beta function for various finite values of m. So for m equals 3, we were at 1.268 here, as I showed. And then this just kept going down, like 1 over m squared. And we were able to fit a curve to this and gain some confidence in this coefficient. So we wrote this coefficient, but through an entirely non-rigorous method. And we did the same thing for anomalous dimensions. And what we found for the anomalous dimensions at the fixed point now was a formula like this. So there are many operators whose anomalous dimension you might want to get. A reasonable subset to look at would be the operators that are Virasoro primaries in the UV, even though Virasoro symmetry is broken by the non-local interaction. So all of the quasi-primaries in the same multiplet can in principle get, well, will almost surely get different anomalous dimensions. But we mostly looked at the Virasoro primaries. And, no, what was it? Yeah, so this, we got some expression like this, where the important part is that it's linear in M. So once again, we see that if M is taken to be large, we can't just plug in small non-zero values of delta and expect to get something sensible. Perturbation theory breaks down again. I didn't want to erase the numerical bootstrap plot. That's okay. So if we're able to do this for the phi22 operator, yeah, how much time do I have? Okay, yeah, that should be enough time. Yeah, if we're going to do this for the phi22 chi deformation, why not other Virasoro primaries times chi? So this is what Dongsheng and Jen and Jake were asking about. In particular, we can look at, so this is for phi22 times chi. What about phi12 times chi? So there are two motivations for doing this. One is that there is actually some evidence that this was showing up in the numerical bootstrap. So I was drawing these regions that had two kinks and telling you that the one on the right happened to correspond to the long-range Ising model. But what about the one on the left? Well, this is a bound on the gap of the first spin 0 operator, but we were also imposing a gap for spin 2 operators. And when you vary that gap, the position of the right kink doesn't change, but the position of the left kink does change. And there's a sufficiently large value of the gap such that this becomes very narrow so that the two kinks merge. But if you make the gap small, in particular if you don't have any gap and you just say that stress tensors are allowed, so local CFTs can also be found in these numerics, then the horizontal position of this kink will move all the way to the left. And then you can look at the vertical position. And the vertical position will correspond to something that makes delta 0 look a lot like the dimension of the 1, 3 operator, which is the first operator other than the identity when you fuse phi12 with itself. So optimistically, we can interpret this as evidence that this line of kinks we get by varying the spin 2 gap ending in the long-range Ising model always gets you to a long-range minimal model where the deformation is by 1,2 times chi. So this is a conjecture that motivated us to look at this. We always knew that if we were going to look at phi22 chi, we would also look at phi12 chi. And there turns out to be post hoc motivation as well, which is that the large M behavior when you look at phi12 chi is going to be much better. And what is that large M behavior? So first I'll write the beta function, which we initially obtained in the same way by doing a fit. And it turned out that we were fitting to something linear. But when we look at the anomalous dimension, we don't have M appearing anymore. So here we get s minus 1 over s plus 1 or s plus 1 over s minus 1, depending on whether r plus s is even or odd. And in this case, we get the opposite. And it looks like that if we set s to 1, it looks like we either get 0 or infinity. Now, the 0 is real, and it actually turns out to be true to all orders. Even at higher loops, the anomalous dimension of r comma 1 will be 0. And this was actually seen in doing these numerical integrals for m equals 3. The infinity is fake, and the infinity is a sign of mixing. So yeah, did I write down what the operator is that mixes? Yeah. So this operator that could potentially get an anomalous dimension that's naively infinite has s set to 1. It mixes with chi times a scalar quasi-primary, which is well defined when r is even, or when r is odd. So this is some combination of Virasoro charges with this weight, which gets you a quasi-primary. And if you fuse phi 1, 2 chi with this operator, you generate phi r1. If you fuse phi 1, 2 chi with phi r1, you generate this operator. So there's a potential for mixing, and that's what leads to this naive divergence. And when you account for this, you get some anomalous dimension, which is finite, and we worked out what it is in a few cases. I won't write down the result. But this is what happens empirically when you compute anomalous dimensions for many values of m and then make a plot. But we would like to get away from that. We would like to get a more rigorous argument that this type of CFT data, which has a nice large m limit, is correct. And there are two ways to go about that. You could try taking m to be large at the very beginning, or you could try taking m to be large at the very end, like we were doing here. So if you take m to be large at the very beginning, you might expect a problem, because this beta function, which involved an integral of a 4-point function, and it gave you something that blows up when you take m to be large. Well, when you take m to be large in this 4-point function, which is built out of Virasoro blocks, you don't get something infinite right away. These Virasoro blocks are well defined at large m. But you do get something where the integral of them blows up. And it turns out to blow up like log a. So this regulated integral where I said we subtract power laws in a, and we get something finite times g cubed, now it's giving us log a times g cubed if we take the large m limit at the very beginning. And that's a divergence, which is problematic, and it's a sign of mixing again. And there's mixing because now, when m is very large, this phi 1, 2 times chi is not the only nearly marginal operator. There's also phi 1, 3. And we have to consider a mixed system of beta functions. So just to write down what the mixed system looks like. we now have this at one loop, and we can find a fixed point at one loop and get it across dimensions. And remarkably, with this one loop analysis and two beta functions, we are able to generate some of the same data we got when we had a two loop analysis with one beta function, where the only difference is that we now take m to infinity first. And there's more mixing to take care of when you do this, of course. So there was only a subset of this data that we attempted to get, but it all matched. And you have to be a bit careful about how you do it, because when we had this plot where we were doing a fit, we were taking the coupling to be very small first, which justified the fact that we were looking at two loops instead of higher loops. And then we were taking m to infinity. So here, I've written it like with a small parameter delta and another small parameter 1 over m. And I did some truncation, which is consistent when delta and 1 over m are of the same order. And what you have to do at the end of the day is compute CFT data using these beta functions, and then look at a limit where it's like more like above, where you take delta and 1 over m to be much smaller than 1, but delta is the smaller of the two. So that is something that works for the phi 1, 2 chi flow, the one that had nice large M behavior. And that's partly related to what Jared was saying, which is that there's a non-invertible symmetry, so you don't have to consider an even bigger system of beta functions. And it's also related to the fact that these OPE coefficients are order 1 numbers. If you tried to do this for phi 2, 2 chi, then you would have more beta functions, more mixing, and you would have some OPE coefficients that fall off like 1 over m, and we couldn't get it to work. But there was something that we could get to work in order to derive this anomalous dimension formula without numerics. And I guess I should spend the rest of the talk explaining that. So are there any questions about this stuff so far? OK. So instead of taking m to infinity at the very beginning, we would like to take m to infinity closer to the end of the calculation, but still not rely on numerics. And it's not obvious that there's a way to do that, but there's a powerful tool in the analysis of minimal models that we haven't tried to use yet, and so we should do that now. And that is the Coulomb gas formalism. So the Coulomb gas theory is a lot like the free boson theory. It's a linear dilaton action. So there's this thing that would just be the standard free CFT, free boson CFT. But then there's also a topological term, which modifies the stress tensor if you vary with respect to the metric. And that modified stress tensor does two things. So it shifts the central charge away from 1, like we want. And it modifies the formula for the scaling dimension of an exponential. So instead of just having conformal weight of alpha squared, it's now alpha times alpha minus 2 alpha naught. So this is enough to capture local minimal models. before we do a deformation with a generalized free theory. So it gives you integral representations of correlation functions in minimal models. And okay, strictly speaking, this action is not enough to do it, but you can deform this action. Well, yeah, you can deform this action by marginal vertex operators, of which there are two. And then use the fact that a vertex operator endpoint function is given by this product formula, where, importantly, the sum of the charges now has to match 2 alpha naught. So the correlation functions that will be non-zero are the ones where you can integrate these marginal operators and then use correlation functions in the free boson theory, or the shifted free boson theory. So to get a correlator of V alpha 1 through V alpha n, you insert V alpha plus the required number of times and V alpha minus the required number of times, and then integrate. And if you use the fact that the central charge is this, which we want to be equal to 1 minus 6 over mm plus 1, then you can easily figure out that alpha plus and alpha minus need to have these expressions, which means that they go to 1 at large M. And if you want it to be possible to get the charge neutrality condition satisfied by inserting these an integer number of times, then these charges, alpha 1 through alpha n, well, they all have to be given in terms of these two Katz indices. And if you plug in these square root formulas for alpha plus and alpha minus, and then convert alpha to the conformal weight, you see that this is nothing but the Katz formula for minimal models. So it's a way of deriving the roots of the Katz determinant. So that's just some basics about the Coulomb gas. I'm going to be schematic and talking about how we used it, but we used it, again, to recover these anomalous dimensions. So the idea is that this 4-point function that we want to integrate to figure out what beta 3 is in the beta function, the coefficient of g cubed, we can write it as an integral representation, as the Coulomb gas would tell us to do. And Coulomb gas integrals, because of this formula here, they turn out to just be Feynman and massless Feynman integrals that have fractional powers here. This alpha I, alpha j might not be an integer. But alpha I, alpha j is an integer when you take alpha plus and alpha minus to 1, i.e. when you go to the large M limit. So from the Coulomb gas point of view, the large M limit is very special. And we can see that by not working directly with a Feynman integral, but instead working with the Mellon-Barnes integral. Because these V alpha plus and V alpha minus operators that we're integrating, those are marginal. So they give you conformal integrals. And when you have a conformal integral, you can use Semantic's formula, which converts star-type configurations to triangle-type configurations, if you like. There might be twos there. So this is the valid way of analytically continuing such integrals found by Semantic, and it requires these integration variables to satisfy a constraint. And by using that as many times as you need to, you can write this 4-point function as an integral where you have many of these variables going along the imaginary axis. You'd have a power of z and a power of 1 minus z. Okay, maybe I'll write. Yeah, because there's enough time. So this is the thing where you've gauged away as much as you can. And then you have a bunch of gamma functions where the arguments are functions of the Mellon variables. And then what you want to do to actually compute a beta function is you want to multiply by a 4-point function of chi as well, and then integrate the whole thing. So multiplying by a 4-point function of chi, that's simple. It just shifts these powers of z and 1 minus z. And then when you integrate, so this is an integral d2z. That's now an easy integral to do when you're in this Mellon form. You have z and 1 minus z, which is just like the simplest Feynman integral. So you can get rid of this and just be left with a Mellon-Barnes integral, potentially one of very high dimension. So now the question is, what does this thing become when you take the large M limit so that alpha plus and alpha minus go to 1? So if these gamma functions were very generic, this wouldn't buy you much. You would just set alpha plus and alpha minus to 1 in these functions, and then you would still have a big integral to do, and it would be very hard to do, and we wouldn't know what the beta function is. But actually what happens in all the cases we looked at is that when alpha plus and alpha minus go to 1, the Mellon-Barnes contour that you're using here becomes pinched, and you have to do some regularization. And the right way to regulate is to initially set alpha plus and alpha minus to other values, and then move the contour out of the dangerous region by picking up some residue. and then take the limit with these going to 1. And what you see is that the residue contribution, which is simpler than the full integral, actually dominates. And that's where the leading large M behavior comes from. And that's why we were able to get these simple expressions like 8/3 of m or 2 over m squared or whatever I wrote before. So if you use this to calculate individual Virasoro blocks, it's possible to find examples where you only have to insert one screening charge. This is the pedagogical example that the yellow book does. Like all sources on the Coulomb gas start out with. And then you're going to have only one Mellon variable to integrate. And you can just do this regularization analytically and see that you get the right answer, because some large M limits of Virasoro blocks are known. If you look at the phi 1,2 chi flow, where you have to insert one screening operator, in that case, you're going to have 2 Mellon variables to deal with. But it's still not too bad. You can either write code or you can do it by hand. And you can see that you get the right answer, the 8/3 of m, or 8/3 pi squared m. When you have phi 2,2 and you have to insert 2 vertex operators, you get 7 Mellon integrals. And then things are very messy, because you regulate 1, you generate a list of lower dimensional integrals, 1 for each residue you pick up. And then each of those needs to be regulated, and you get this exponentially growing tree of integrals. And the only sensible way we could find of doing this was to go back to 2005 and use the Mellon-Barnes package mb.m, which we could run for a few hours, and then get computer-assisted proofs of the beta function and anomalous dimension formulas I was writing down, which are as rigorous as the Coulomb gas is, which I'm told is not completely rigorous. But that is a way to get the large M behavior of these minimal models, of these long-range minimal models, and perhaps other long-range minimal models. Although if you make these CAS indices much larger than 2 and 2, I shudder to think of how long this would run and how much memory it would consume. But then again, this is from 2005. So maybe the Feynman integral community would have things to say for speeding this up, either using some modern insights or just the fact that minimal models behave a bit differently from the integrals that this was written for. It's possible that there's more untapped potential here. So there are these two types of long-range minimal models that we looked at, where one of them has nice large M behavior, and the other one has a known dual description. And it would be nice to find a dual description for the one that does have nice large M behavior. And something you can do when you're perturbing exactly solved CFTs in 2 dimensions, like minimal models, is you can use Hamiltonian truncation. And to get some intuition for what happens as you make the coupling of this deforming operator phi 1,2 chi large, that might be an option. And there are even applications of Hamiltonian truncation in 3 dimensions. So if we plot some operator dimensions going from small to large epsilon, so let's say we're in 3D. We have this operator phi, which has dimension 3/4 at epsilon equals 0, and then we have phi cubed, where this would be 3 times as big. So 3 minus this. And then they have to always add up to 3 and move linearly. And what you might imagine is that the lines cross and end up in the same place. But this, of course, does not happen. There's a crossover that you hit before that when this becomes when sorry, I did this backwards. Yeah, so maybe I won't dwell on that. Instead of the deformation I've mostly been talking about in 3D, sigma times chi, we can consider epsilon times chi, where there's much less distance between these two operators. So one of them starts off at 1.6, the other starts off at 1.4. So epsilon is here, chi is here. And then as you raise the coupling, these are already fairly close, so there's less of a chance naively that you're going to hit some other crossover. And maybe what happens is that when this chi gets to be 1.4 or 1.41 or whatever it is, you can interpret this as being now the energy operator of a short-range 3D Ising model, and then interpret this as being a generalized free field, and observe some kind of self-duality, where at large enough coupling, the theory becomes the same as what it was at small coupling. Now, this is a very bold conjecture, and I don't know any way to get evidence for it yet besides doing Hamiltonian truncation. So I propose trying to prove or disprove this using Hamiltonian truncation. And then I also think that analysis should be applied to some very general phi RS chi deformations of minimal models in 2D, because there's a well-known staircase flow connecting minimal models in the local case, known for a long time by Zemolodchikov. And if the minimal models are unitary, it's sort of obvious that any flow going from one to the other is going to reach another minimal model if it reaches a fixed point at all, because these are the only unitary CFTs with central charge less than 1, and the C theorem tells you that the central charge needs to keep going down. But there's an unreasonable effectiveness of minimal models that's been observed in recent years, where even in the non-unitary case, minimal model deformations by other operators like phi 1.5 and phi 1.7 and so on have also been shown to close among themselves. So there's some work by Federico and Stefano indicating that maybe we need to relax our notion of integrability and find some other ideas that really explain why these minimal model flows close amongst each other in the local case. I think Jared knows more about what they're proposing. They have these integral equations for these non-integrable flows that yeah, I need to check the paper again. They have some arguments that these flows might be integrable in some kind of weaker sense. I don't remember more than that. Okay. Yeah, so that provides a hint that maybe these higher phi RS deformations that define other long-range minimal models could have some nice behavior when you make the coupling large instead of small. I don't know what to expect yet, but I think it's interesting to investigate. yeah, I think these are the future directions I wanted to get to. So thanks for listening.
I can just first ask a question, maybe you don't have to draw it again. So you said that if you take the spin cap exactly at 2, then you recover this dimension of phi 1.
Yeah.
And if you make the spin cap slightly larger, this kink is then move again. The second kink, were you able to kind of, with the perturbative results that you got now, match it to the second kink?
No, that's a motivation to do more numerics, because yeah, in our paper we had essentially just the values that we showed, and then we figured out what the extreme left values were, but we had very little data in between. And yeah, now that there's stuff to compare to, we need this data. So I did miss a future direction. That's good.